Quite long title, so what you have to remember is this short title on the bottom of the slide. So PFM for dissipative PHS. I will explain what this means. This is a joint work with Denis Matignon and our PhD student Anass Serhani, and we work very far from here at Isaïe Superior on the other side of the road. And so the aim of this work is to preserve something when we deal with partial derivative equation. So I will start with the introduction. In this introduction, I will start by explain what we want to preserve exactly and how to do it in I will explain it by hand without assumption. And then we will focus on the wave equation. First, by present the method and then extend it to dissipative system. So our objective is to simulate complex open physical system ensuring the conservation of some power balance for a chosen functional. And this functional is exactly the Hamiltonian. So to do it, we choose to use finite element methods, which is robust, well-known, and port-Hamiltonian system. Why we do that? Because it split complex system into simpler one. And the energy, so the Hamiltonian we want to preserve, is exchanged between this simpler subsystem. And the power balance is encoded, in some sense, in a Stokes-Dirac structure in this formalism. And this using the partition finite element method, so I will say PFM from now on. It translates the Stokes-Dirac structure in infinite dimension into a Dirac structure. And this allows to get directly a discrete power balance. And this idea was first appear in this proceedings in Lagrangian and Hamiltonian method for nonlinear control past year. So this means that we need some kind of change of paradigm to work from physical system, open, complex physical system, to get until the simulation. So you start with a context and axiomatics, so conservation of mass, for instance, and on the other side you have definitional laws coming from assumption on your experiment. So and what we are interested in is the evolution of some sort of energy, the Hamiltonian, which can also be the entropy, depending on what you want to observe. So usually in the PDE community, we mix both, meaning that we plug directly the laws into the equation here, obtain PDE, and then apply the finite element method. So the question is, in that manner, how I define my discrete Hamiltonian, or it evolve, or does it evolve? So we use port-Hamiltonian system because it split the system into two distinct parts. The first one is the structure coming from the context and axiomatics. The second one is the constitutive relation. And using this structure, avoiding the substitution, we perform the finite element on each part. Doing that, we have canonical discrete Hamiltonian. This is designed for control at the beginning, directly here, and this is well suited for coupling since this is the idea of PHS. The difficulties that arise, because everything has a price, is that it's become a differential algebraic equation. So some definition and notation. First, what is a port-Hamiltonian system? A dissipative port-Hamiltonian system, in general, when you open a book, this is energy variables and the Hamiltonian. You can define from that the co-energy variables, which are the variational derivative of the Hamiltonian. You have a structure operator, which is formally skew symmetric, a resistive operator, which is positive, a control operator, an input to apply with this control operator, and a collocated output given by the control operator. Then you deal with this dynamical system, which makes appear here the dissipation, because R is positive and here there is minus. So doing this, we get directly this lossy power balance, meaning that the variation of the Hamiltonian along time is given by this equality, and since R is positive, this is less than the power supplied to the system. So of course, if you want to solve this system, you need some relation between the energy and co-energy variables called the constitutive relation. So this is a closure equation. Now, the structure that we want to preserve to obtain at the discrete level the lossy power balance is the following one. You have a space of efforts where we define this vector, and you add here what we call a resistive port. You take its topological dual. You define this input-output structure operator. So input-output because it contains the input control, the input operator and the output operator. You define the bond space, which comes from the space of flow and the space of effort, using this bilinear product. You define now a maximal isotropic subspace coming from the graph of the structure operator. And of course, since I add two unknowns and only one equation in J, I must add the dissipative constitutive relation, which may appear the operator R. So we kick out the dissipation out of the structure we want to preserve. So now if you have a trajectory in the Dirac structure, you have this equality. So imagine that you are able to solve your problem. So you have here a trajectory in the Dirac structure. If you add the dissipative constitutive relation, you directly obtain the lossy power balance equation. And this way to write with flow and effort generalize the G minus R representation. And we can use it we will use it to get a discrete version of the lossy power balance. So let us begin by recalling what is PFM on a conservative system. So we will talk about the wave equation, so the deflection of a membrane. The Hamiltonian will be the total energy given by the potential and kinetic energy, where ρ and T are physical parameters. Alpha will be the linear momentum, alpha P is the linear momentum, and alpha Q the strain. Performing the variational derivative, we obtain the stress and the deflection velocity, and we want to control the deflection velocity at the boundary of the membrane. So the first remark is that every variable has a physical meaning. The second remark is that we do not make assumption like a constant Young modulus or constant mass density. Now the output is given by the dual of this operator on the boundary. So this is given by the normal stress. You know the wave equation is written usually with the deflection W here, making appear the physical parameters. If t is constant, it comes out and you get back the classical Laplacian. But I want to use this physically sounded object. So I will write it in the port-Hamiltonian formalism, that is using the energy variables against the co-energy variables. Here you can see that you have some kind of J structure operator. And you get directly this lossless power balance, which says that the total energy is preserved. Sorry, the variation of the total energy equals the power supplied to the system. And now PFM, the strategy of PFM is quite simple and straightforward. First, you write the real formulation of your system. Secondly, you apply the green formula on one of the energy variables equation in order to make appear the control you want to apply. And then you apply finite element method. So let us do it. You have the wave equation. I wrote the weak formulation. I apply the Green's formula on the first line. So here you have the boundary value of EP at the. So this is exactly the control we want to apply. And if we perform the Green's formula on the second line, in fact, we control the normal stress. Then we use finite element family. No assumption for the moment. The only thing is that this family is constituted of vector-valued shape function. So you can define an approximation of the strain like this. You do the same in the same family for the stress. You do the same for the linear momentum and the velocity, and also for the boundary variables. Okay, we end up with this system where all the matrices are classical, so mass matrices. And you have here rectangular matrices which discretize, in fact, the gradient and the divergence. Again, a remark, this is the structure. So in all these matrices, you do not have any physical parameters. Any physical parameters are kicked out in the constitutive relation. For the structure, we don't want to know how the system is. So if I rewrite everything, I get this structure operator. It is skew joint. I take its graph. This is a Dirac structure. If I take the appropriate inner product on the finite dimensional spaces. Okay, so this appropriate inner product is given by the mass matrices. Now the discrete Hamiltonian is directly defined by substitution of the approximation into the continuous Hamiltonian. You get the discrete one with the coefficient and the finite element family. We end up with this, where these matrices are mass matrices weighted by the physical parameters. And the constitutive relation comes using the finite element method. You write the weak formulation, you project, you obtain this. At the end, if you have trajectory in the Dirac structure, the discrete Dirac structure, then this scalar product with respect to the mass matrices is equal to 0, and you end up with a discrete lossless power balance. Okay, that was on the conservative system. Now, what if the system is dissipative? So let us start with internal dissipation. So we have epsilon here, which is positive. And this modifies the equation like this. You add here the minus epsilon EP. I write down the system under this form. So we can see that this is exactly J minus R, where J is formally skew-symmetric thanks to Green's formula. And if I add dissipative port FR and ER and a dissipative constitutive relation ER equal epsilon FR, so I kick out again the physical parameter epsilon out of the structure, I obtain this structure operator, and the lossy power balance is given by this, where the stem is negative. And we want to mimic that at the discrete level. Okay. I apply PFM, like in the previous slide, and I directly obtain this big system with mass matrices on the left and skew-symmetric structure operator on the right. I add the dissipative constitutive relation, always by the classical finite element method. So the big capital E is an average mass matrices weighted by the dissipation. You obtain an extended Dirac structure which takes into account this epsilon, but only with this dissipative constitutive relation. So you look at the time derivative of the discrete Hamiltonian. You use the dissipative constitutive relation, and you end up with the discrete lossy power balance. Okay, so this is not too difficult to do it when this is internal dissipation, because this is J minus R. So this seems quite straightforward. Now, if we want to take into account boundary dissipation, and especially impedance boundary condition, which I will say IBC. So you have a boundary function Z, which is positive, a new control nu, and you want to apply this boundary condition. You control this boundary condition. So what is this? If Z equals 0, you come back to the previous case, and this is Dirichlet boundary condition. If Z tends to infinity, you get, in fact, Neumann boundary condition. So this kind of boundary condition interpolates between the two conservative cases, Dirichlet boundary, and in fact, in acoustic, this is the way to pass from hard wall to soft wall. So this has a physical meaning. But this is not easy to, it's not really easy to fit in the J minus R framework. So how can we do it? In fact, if you look at this equation, you can see that this is the U of the previous slide, and this is the Y of the previous slide. So in fact, this is an output feedback law. Okay? Well, if this is an output feedback law, I directly obtain this lossy power balance. And if I apply PFM, so I introduce impedance port, taking into account Z, together with this dissipative constitutive relation, which again kick out the physical parameter out of the structure. you end up with this big system, which is with these additional constitutive relation. And if you look at the discrete, the variation of the discrete Hamiltonian, you can see that it mimics perfectly the continuous one. This is the last one. So now we just would like to know if what we wrote on paper works. So we took an heterogeneous case, anisotropic on this rectangle. We do not put inside internal dissipation. And Z will be switching only at t equal 2. So at the beginning, it must be a constant Hamiltonian, and at time 2, it must decay until it reaches a stationary solution. So on the left, you have the deflection. On the right, the stress. And at t equals 0, equal to, you decrease until you reach a stationary solution, because with IBC, 0 is always an eigenvalue. Conclusion, just a word to sum up. This work also for heat equation. This work also for shallow water equation, the same method. And actually we work on the first two items. So how to choose a finite element accordingly to some wanted property, such as convergence rate. What to do when I want to apply different types of control depending on the part of the boundary. And something we are not aware of, what about symplectic time integration when we are dealing with differential algebraic equation? Thank you.